Hello, my name is Martin Kronberg. Welcome to the IoT Developer Show, Season 4. In this episode, we see how to use Intel's FPGA-based Vision Accelerator with the Intel Distribution of OpenVINO toolkit. We also learn a bit more about the hardware architecture programmed in the FPGA and how it works. The first thing to remember is that the FPGA-based accelerator works seamlessly with the Intel Distribution of OpenVINO toolkit. Once the code is written, it can be targeted to run at CPU, integrated GPU, VPU, and FPGA with the appropriate plugin. For FPGA acceleration, the device must be configured at runtime with a bitstream, which implements the desired network topology, such as GoogleNet, ResNet, MobileNet, and so forth. Every release of the Intel Distribution of OpenVINO toolkit includes several pre-built FPGA bitstreams, which have been optimized for one or more network topologies. When you load the FPGA plugin, you can specify a fallback device. For instance, in this code snippet, we see FPGA specified as the main inference engine and CPU as a fallback. So if a layer isn't supported on FPGA, it will be run on CPU. The bitstream loaded into the FPGA contains Intel's deep learning accelerator design, which runs the actual vision inference. The DLA engine is comprised of the following elements: a feature map cache for input images, output images, and filter data, an array of convolutional processing elements which use dot product operations to implement matrix math, a crossbar switch which connects processing primitives such as pooling, normalization, and rectified linear unit, or ReLU, a memory interface to external SD-RAM, and finally, a configuration engine which controls the system at runtime. Now that we have an idea of what the DLA is, let's take a look at an example of how the engine works. The feature map cache is used to load in the 3D tensor for processing. Initially, this tensor is simply the input image. The convolutional layer uses a small 2D filter and performs a dot product with the input to output a feature map. The filter is then applied across the rest of the input feature map to produce a 2D output. To generate multiple output channels, we apply multiple filters at the same time, one for each color channel, for example, RGB. With the DLA, we can combine multiple layers into a single pass. Here we see the process in action with the AlexNet topology. The output of one pass becomes the input to the next and proceeds until the entire network is complete. FPGAs can be designed to perform many operations in parallel. The DLA processing elements operate in parallel and execute multiple filters on the same convolutional layer. This is known as K-vectorization and leads to an increase in performance. The DLA design also highlights the flexibility of an FPGA. We can use the DLA to add new primitives to the topology when needed. We can also tune the DLA to adjust how much on-chip memory and multiplier resources are allocated between the processing elements array and feature map, once again tuning the performance. FPGAs also support complementary functions to vision inference such as encryption, networking, pre- and post-processing, and I/O ingestion. These enhancements provide flexibility to meet new performance and functionality requirements. To gain a deeper understanding of the DLA architecture, you can watch the online training module or download the white paper in the links provided. Join us next time where we wrap up Season 4 of the IoT Developer Show. Thanks for watching.
Hey everyone, thanks for watching this video. If you liked it and haven't seen any of our other videos, subscribe to the Intel Software YouTube channel. You can also connect with other developers and enthusiasts in the comments, and we'll see you all next time.